Okay, I'd like to tell you about how to find the electric field um, for an insulating sphere that's charged up. So let's say the sphere is not a metal but an insulator, maybe made out of wood or styrofoam or plastic or something. And let's say the charge is embedded evenly throughout here. So you have a bunch of charge that's embedded evenly throughout here. Okay, in fact, let's say that the charge density, that's going to give that a term rho. Rho is the charge per volume. So, for instance, if you know the volume that you're talking about and you know rho, then the charge is going to be, just bring the V on the other side, rho times V will be the charge in that volume. So if you know the density of charge and you multiply by the volume of the charge, you get Q. All right, so let's say I want to know what the field is a distance r away. Let's have the r of the whole thing be capital R. That's going out to the edge. But we want to know, like, what's the electric field? What is the electric field when you're just a distance r away and r is smaller than capital R? Okay, so what we do is we draw a Gaussian sphere. This is a Gaussian sphere. Um, and then we just apply Gauss's law. So the total charge enclosed by this Gaussian sphere over epsilon naught, that's the net flux. So the net flux is the total charge enclosed by the Gaussian sphere over epsilon naught. But the net flux for this surface, this Gaussian surface, is also equal to the closed surface integral of E dot dA, where you add up all the little fluxes through all the little windows, all the little dAs. Okay, well, the charge enclosed by this is going to be just, if we know that the charge is uniformly distributed, rho, then it's going to be rho times the volume. Now the volume of this sphere is 4/3 times pi times little r cubed, not big R cubed. This has got a small radius cubed. So that's rho times volume over epsilon naught. This is Q enclosed. That's the volume. This whole thing is the Q enclosed over epsilon naught. Now, if you're here, the dA for this thing points this way, and so does the electric field. The electric field points straight out. All this charge negates itself. So if I put a positive charge, say right here, right there, it gets pushed down by this stuff. All this stuff pushes it down, and all this stuff over here on the outside pushes it up, and they negate one another. And so the only electric field that there is then on here is just due to this stuff right in here, this stuff. And so that's going to equal, I can get rid of the dot product because dA is this way and so is E. And so I'm going to get rid of that dot product. Do the same steps every time. And that's because E is parallel to dA. That's the argument at all points on the Gaussian surface. And then what we're going to do is we're going to pull the E out, because the E is the same here as here as here as here. It's the same at every point on that Gaussian surface because of symmetry. Why would we expect it to be bigger here than there? The symmetry arguments say that there's no difference between this spot and this spot. And so when we pull those out, the E out, and I sum up all the dAs, I'm going to sum up all the dAs, and when I do that I get 4 pi little r squared Those are, when you sum up all these little dAs around your Gaussian surface, you get 4 pi little r squared. And that's equal to rho 4/3 pi r cubed over epsilon naught. Okay, well, let's get rid of a pi. Let's get rid of an r squared. Let's get rid of a 4. And it looks like, I can put this over here, it looks like when I get all done, E is equal to rho r over 3 epsilon naught. See how that works? In fact, if I were going to graph this, if I were going to graph how that looks, that's a constant, the 3 is a constant, the rho is a constant, and so this is like the equation y equals mx plus b. Let me explain. If we found out that the E in there was rho r over 3 epsilon naught. So that's like the equation y equals mx plus b, but b is 0. There is no b-intercept. So that's the slope of the graph. So if I plot E versus r, but then this is just going to go straight up like that. Now that's inside. That's up till we get to r. That's up to capital R. Now you might think, well, what is it outside the sphere? So let's find that right away. Okay, so remember we have a charge that's rho. We have a sphere that has a charge density of rho. It's charged up in here. It's throughout. The charge is spread out throughout. And I want to know the field right here. A distance lowercase r again, because that's a variable. And this is capital R. Okay, to get the field right here, I'm going to draw a Gaussian surface. That's going to be a sphere. And I'll apply Gauss's law. Okay, so the Gauss's law is that total charge enclosed over epsilon naught is equal to the closed surface integral of E dot dA. Okay, the total charge enclosed is going to be rho times this volume now, the whole volume. So that's going to be 4/3 pi big R cubed, since this is big R, all over epsilon naught. See how that gets you the charge enclosed? See, the charge doesn't go out all the way to here, does it? It stops. The charge stops right there. Okay, on this side then, we can get rid of the dot product because E is parallel to dA. And E is the same at every point on here. E is the same. So that's going to be just E times A, but when you pull out the E, you add up all the dAs. The A is going to be 4 pi r squared. Now which r is it? It's the little r. See how the surface area of this is 4 pi little r squared? So we get rid of a pi and a 4. And it looks like we get that the electric field when we solve for this is equal to rho r cubed over 3 epsilon naught r squared. Okay, well, these are all constants. Let me circle. Everything there is a constant except the r squared, the little r squared. The big R cubed is just the radius of the whole thing. And so if we wanted to plot that, that's a 1 over r squared graph. So when you get outside, it shoots down like this, just like a 1 over r squared graph does. Okay, so that's the electric field for an insulating sphere. Thanks.